Okay. Asynchronous week 7. We're almost done, you guys. This is actually the last section we're going to cover in chapter 5. It's section 5 for the method of substitution. It's incredibly important heading into Calc 2 that you understand how to evaluate integrals using substitution. So I'm going to go through that. The first half of this using indefinite integrals right now. And then on Monday, we'll add in some definite integrals to this. There won't be like a ton more to do Monday, but definitely there's definitely more to do when you add in the definite integrals. Let's see, I'm looking through my examples here. Yeah. Oh, and then on Monday, I'm going to add in just a few more types that you're going to see of these. So nothing super crazy. So I'm kind of splitting this in half. Probably the bulk of this you'll see today, though. All right. Method of substitution. I'm going to give you the theorem. And if the theorem doesn't make sense to you, I think the process will come pretty easily to you for the most part. Oh, and by the way, I have to point out my integration by substitution shirt. Just do it. DU. We're going to be using U. I love this shirt. Have to wear it when I teach this section. All right. If capital F prime of x equals f of x, then the integral of little f of u of x, so this is a composite function, times u prime of x dx equals the antiderivative, big U, of u of x plus c. This is really kind of like the chain rule in reverse. It's very important. Okay. So this is going to be when you're trying to integrate some sort of composite function. So far, I really haven't given you hardly any integration rules. You've basically just worked backwards from derivatives. I gave you a power rule, which again was still just working backwards from a derivative. And then we talked about recognizing like trig function derivatives and just kind of integrating backwards from there. So this is going to be for situations where we have composite functions. And it's going to be really important, you'll notice as we go through the examples, that we actually have the correct form. Integration is much trickier than taking a derivative. I mentioned this before. Taking a derivative, you can just kind of push your way through most of the time by brute force, and sometimes that might be a lot of work, but you can still eventually find the derivative. Integration is trickier just because you have to be able to match a certain form. Even for this method of substitution, there's only so much you can do to work around, and some of these I mean, nothing's going to get super crazy here in 5.5, but there are some really hairy integrals in this world. ACC, back before COVID, used to have these integration contests every fall and spring. That's how much of a skill it is to be able to integrate functions. Students would show up for the integration contest, and then they would just go through rounds of integrals until eventually we got first, second, and third place winners. It was like elimination rounds. So integration is a process. It takes a while to learn just because there are so many different forms to fit. So when you go through these different exercises here, you're trying to use the method of substitution. In Calc 2, you're going to use a whole bunch more methods that you're going to learn. So this even still is a little bit just more basic. Okay. So our first example is the integral of x times the quantity x squared plus 1 cubed dx. Now, technically, you could go through here. You could cube x squared plus 1 and then multiply it by x, and then you could use the power rule. But that would be a lot of work. So you're going to use the method of substitution here in order to find this integral much more quickly. In order to do that, you first need to make sure that you have everything you need to match this form. The first thing you're going to identify is an inside function. So if we're thinking about composite functions, just like we did when we used the chain rule for derivatives, you're going to do the same thing here, thinking about which function's on the inside, which one's on the outside. So if I'm looking at this quantity, x squared plus 1 cubed, my inside function is x squared plus 1. Not the cubed part, just the x squared plus 1. Now notice, looking at this theorem that I gave you, you're taking f of some function u of x and multiplying it by the derivative. That's basically what we're going to turn this into. So if your big function is x cubed and your inside function is x squared plus 1, I should have said, let's let u of x be x squared plus 1, and then f would be x cubed. This is just the composite function that we're going to undo. So here's where the u substitution comes in. You're always going to let u be your inside function. So it's really important that you're able to properly identify that. So in our case, u is going to be x squared plus 1. And what I need to find here is inside this integral, I need a u prime of x dx. I need to force it to be there. So if I'm looking for u prime, and it kind of depends on how you want to write this, I tend to use a du, but that's up to you. Take the derivative of u, and you get 2x dx. Now, the reason I write it like this is because I want it to match what's in my integral. Yes, technically, we would normally say du dx is 2x, but I want the dx to be on the integral too. So you're going to look at the integral and see what you have. You have an inside function cubed, and then you also have, in addition to that, an x dx. What you don't have is a 2x dx. You don't have two of them, you just have one of them. So what you're going to do is you're just going to match this up so that you have just x dx. And to do that, you're going to divide both sides by 2. You get 1/2 du is x dx. And this is going to take care of the x dx portion of your integral. Now, watch what happens as I rewrite this. And if you'd like, I'll include an intermediate step. If it helps to see these sort of separated, you can rewrite the factors so that the x is right next to the dx. Sometimes that just makes things easier to see, especially when this is new. So I'm going to replace x dx with 1/2 du, and I'm going to replace x squared plus 1 cubed with u cubed. So I'm just using the u substitution that I just built. So u is x squared plus 1. X squared plus 1 cubed is then going to be u cubed. And x dx is now going to be 1/2 du. Now notice that we're using a du in this integral because that's going to be our variable of integration. We always have to match up this variable to whatever we're trying to integrate. And in this case, that's a u. If you want to take this 1/2 and pull it out front because it's a constant multiple in this case, that's fine, do that. And now we have 1/2 times the integral of u cubed du. And now we can just use the power rule, integrate this with respect to u, and then back substitute for x. So if it helps you to have this labeled, the x dx was the 1/2 du, and this piece right here is u cubed. So that's where all of these parts came from. Make sure that everything is accounted for, that you've replaced everything, and once you have, you can go ahead and use the power rule to integrate. So we're going to take u to the 4th divided by 4. And I know we spent a lot of time already talking about definite integrals last time, so get back into the habit of writing your plus c's for your indefinite integrals. I'm going to simplify this, and then we're going to back substitute for x because I don't want my answer written in terms of u. So this is 1/8 u to the 4th plus c. And once you're here and everything is simplified, just go ahead and switch out your u again. Remember that we originally said that u was x squared plus 1. So we're going to write this as x squared plus 1 to the 4th plus c. And notice, by the way, now you have this nice, concise answer. It's nice and neatly condensed together. If you would have, from the beginning, cubed this out, multiplied it by x, and used the power rule on it, you would get an equivalent answer, but it wouldn't be this nicely compacted form. So that's how you use the method of substitution to integrate composite functions. So the key is, whatever your inside function is, you have to have the derivative sitting in there somewhere, or at least the variable portion of the derivative. And if you don't, I'll show you some examples where we sort of have to create it. Sometimes you can, sometimes you can't. Everything here is going to be given to you such that you can integrate it using substitution. Example 2. So this one is the integral of x plus 2 to the 4th power dx. Now we're going to go ahead and look again for the inside function. Now notice you don't have any additional factors of x in this one like you did in the last problem. That's okay. You probably don't need it, because notice that your inside function, and usually students are pretty quick to identify that, is just the quantity that's inside the parentheses in most cases. U is going to be x plus 2 here. And again, you could take x plus 2 to the 4th power, which, by the way, is not x to the 4th plus 2 to the 4th. You would have to actually multiply x plus 2 by itself 4 times. Just a reminder. So this is not so straightforward. But for substitution, we don't need to go through all that. We can just let u be the inside function, and du, the derivative of u, is just, well, it's 1 dx, because the derivative of x is 1. So du is dx. And now you can do a direct substitution here, because everything is accounted for. So we're going to replace this quantity with u to the 4th, and we're going to replace this quantity with du. And this one's actually a simpler problem than example 1. Now we're going to integrate, then we'll simplify if needed and back substitute for x. So this is going to be 1/5 u to the 5th. Don't forget your plus c. And then back substitute for x. We said that u is x plus 2. So we'll make that substitution back in for x. And this one's done. Now I want you to notice the difference between example 1 and example 2. The main difference here is that for example 2, even though it looks like all you had to do was increase the power by 1 and divide by the new power, essentially that was what you did, that only worked because du was 1 dx. That would not have worked in example 1. We couldn't just take x squared plus 1 to the 4th power and divide it by 4. Your constant multiple would have been off in that case, because even though you had the x, we needed this 1/2 to make our substitution. So I just wanted to make sure to note that this is not a situation where we're just taking the inside function to the n plus 1 power and dividing by n plus 1. And this is going to look a little bit different when we move away from polynomial functions also. Because remember, we usually just start out with polynomials. I have some radicals for you next. And then some rationals. It's all good stuff. Okay. Example 3. So this is the integral of x squared times the square root of x cubed plus 4 dx. Okay, now if you would like, you can always rewrite the radical as the 1/2 power. You're probably going to want to do that anyway, since you're going to have to integrate here at some point. So if you want to do that now, that's fine. If you like to see parentheses versus a radical, that's fine. But when we're looking at your inside function, in this case, I mean, clearly in this case you have parentheses, so you would consider the function inside the parentheses. But if you have a radical, your inside function is most often just going to be the expression in the radicand. So let's take your inside function as x cubed plus 4. And remember that we need to create this derivative, x squared dx. Now, you're going to start to see a pattern here with these substitution problems. When you make the substitution for polynomials like this, you're going to be looking to have a situation where your derivative is decreased by a power of 1. So you have x cubed, and then the derivative that's sitting here on the outside is x squared, because when you take a derivative, you decrease the power by 1. So you're going to start to get a feel for when you can and when you can't use substitution in an integral. Du is 3x squared dx. And then you're going to look back at your integral and notice, like, wait a second, I don't have 3x squared dx. I just have x squared dx. Fine. Divide both sides by 3. When you divide by 3, you multiply by 1/3. And now you have x squared dx is 1/3 du. So these two together, x squared dx, are 1/3 du. And this quantity right here is going to be u to the 1/2 power. Everything is accounted for, and that's what's important. There's nothing that we missed. There's nothing extra. So I'm going to take the 1/3 and I'm going to place it in front. And then I have u to the 1/2 du. Now, sometimes this bothers students when they notice that, like, wait a second, I had an x squared. What happened to it? Remember, that's part of your du here, your 1/3 du. So I know it seems like you lost something. You really didn't lose anything. Everything is covered. You have a 1/3 du, and then you have a u to the 1/2. That's all. I mean, look, it's all accounted for. So I realize that it can seem upsetting that you're losing something on here, losing a variable factor, but you didn't. It's covered. All right, increase the exponent by 1 and divide by the new power. So u to the 3/2 divided by 3/2 plus c. Dividing by 3/2 is like multiplying by 2/3. So be careful here not to just automatically cancel the 3's, because you actually can't cancel them in this instance. And you've got 2/9 u to the 3/2 plus c. And now back substitute for x. We said that u was x cubed plus 4. Once you back substitute, you'll have 2/9 times the quantity x cubed plus 4 to the 3/2 power plus c. And that one's done. And again, this was definitely not a case where you're just adding 1 to the exponent and dividing by the new exponent, because you had this whole situation here that had to get substituted out. Example 4, we'll do a rational function. The numerator is x plus 3. The denominator is x squared plus 6x quantity squared dx. Okay, now this one's a little different because your inside function's in the denominator. I'm not too worried about you being able to locate the inside function. Usually students are pretty good at that. It's this quantity in the denominator that's being squared. So you're going to let u be x squared plus 6x. Now we're trying to create what's left over in this function, which is an x plus 3 and a dx. So take the derivative of u and you'll get 2x plus 6. Now this is a binomial, so I put parentheses around this just so that's clear. Now I'm trying to get x plus 3 dx, but I don't have that. I have 2x plus 6 dx. Notice, however, that if you factor out a 2, you can come up with this x plus 3 dx that you're looking for. Now divide both sides by 2. And now you've got a substitution for your numerator. X plus 3 dx is going to be 1/2 du. And the denominator we already know now is u squared. Now if you'd like, I can write this a little bit differently so that it's really clear where everything's supposed to go. But when you have a fraction, the dx technically gets multiplied into the numerator because it's, not in the denominator of a fraction. So really, you could, if you wanted to, rewrite your integral like this. These are the same thing. You're just saying the same thing in a different way. But if you find that helpful for making your substitution, then do it. Sometimes it's easier just to have dx in the numerator, so it very clearly, you can see the substitution more clearly. So 1/2 du gets substituted out in the numerator. And then in the denominator, we have x squared plus 6x quantity squared. Well, that's u squared. Now, in order to integrate this, we're going to rewrite this a little bit. Like, first of all, I don't want to have a u squared in the denominator. My goal is to use that power rule here. So I'm going to move that up into the numerator, and I'm going to take the 1/2 and I'm going to put it in front of the function. So I have 1/2 times the integral of u to the -2 du. And then we'll integrate with respect to u. Increase the power by 1. Divide by the new exponent. Add c. Okay. So now the -1 is getting multiplied by the 1/2. Whether you divide it or multiply it is not going to make a difference. So we'll have -1/2 times 1/u plus c. And if you like, if you think it looks better, just write it as -1 divided by 2u plus c. Lots of different ways we can rewrite this to make it look better. Up to you. And then we'll back substitute for x. The quantity u is going to be x squared plus 6x. Don't forget your parentheses if you move that 2 into the denominator. Now here is your integral. See what I have in store for you next. All right. So next I'm going to show you some situations where the substitution doesn't fit on its own. You kind of have to force it to fit, but it's not too big of a stretch. Like, it's not some crazy thing you have to do. It's just a slight adjustment. So we'll do a couple of those. I need to start noting what time I started these videos because I never want them to go for like super long time. I have an idea, but need to. I know here we are on Async week 7, and I'm finally getting to the point where I'm realizing I need to note the time I started the videos. All right, example 5. This is the integral of x divided by the square root of x plus 1 dx. Okay, now if it helps for you to write the denominator to the 1/2 power, that's fine. You don't have to. If you want to wait on that, I would wait personally. I feel like it's pretty obvious that the radicand is u. So u is going to be equal to x plus 1. Now what I'm trying to come up with my derivative here is x dx. So I need to sub out the x that I have and the dx. Well, note, however, that when you take the derivative of u, the derivative of x is 1 dx. So if I tried to substitute this out, I would still have an x in the numerator divided by the square root of u times du. So the dx gets swapped out with the du. The square root of x plus 1 gets swapped out with the square root of u, but I still have this leftover x. That's not the end of the world, however, because notice that I already gave you an expression that includes x in it. So what we're going to do is kind of like a double substitution. So if you know that u is x plus 1, well, we can solve for x and say that x is u minus 1. Sorry, I can't figure out how to get this cord to go anywhere except in my camera view. Terrible. Okay, so if u is x plus 1, x then subtract 1 from both sides, x is u minus 1. So when we make this substitution again, we can sub out x with u minus 1. Now everything's written in terms of u, which is exactly what we want. So you can see now why it's really important to be careful to make sure that we've covered everything and substituted the variable wherever we see it. Now, this looks like an example of a problem that we would have done in 4.8. We did several of these where we had to split up the fraction. So let's go ahead and do that. So you have u minus 1 divided by the square root of u. I'm just going to take this out of the integral for a minute. This is u divided by the square root of u minus 1 divided by the square root of u. Okay, I'll just rewrite both of these. Why not? And then I have u to the 1 minus a half minus u to the negative 1/2. Remember, if you're dividing and you have the same base, you subtract the exponents. And then with this one, we just bring the u up to the numerator, and the positive exponent will switch signs and become negative. So this leaves us with u to the 1/2 minus u to the negative 1/2. And now we're ready to integrate. So we took the integrand and we rewrote it. So we have u to the 1/2 minus u to the negative 1/2 du. Okay, now we'll integrate the way that we normally would. Anytime we're taking an antiderivative, increase the power by 1, divide by the new exponent. Increase the power by 1, divide by the new exponent. Add c. So my suggestion is simplify first and then back substitute for x. So this will be 2/3 u to the 3/2 minus 2 u to the 1/2 plus c. And we said way back when that u was equal to x plus 1. So we're going to sub back in for x. So we have 2/3 times x plus 1 to the 3/2 minus twice x plus 1 to the 1/2 plus c. Example 6 is x squared divided by the quantity x plus 1 cubed dx. Okay. Your inside function is the one that's being cubed, so that would be x plus 1. The derivative of u is 1 dx. So note that if you were to make this substitution here, in the denominator, you would have u cubed, and dx would be subbed out for du, but you would still have an x squared in the numerator that hasn't been taken care of, and that's fine. Use the same process that we did in example 5. Write x as a function of u. So x would be equal to u minus 1. And note, however, that you need x squared, which is fine. If x is u minus 1, then x squared is u minus 1 quantity squared, which is u squared minus 2u plus 1. And then you can put this back into your integral. X squared is u squared minus 2u plus 1. You're dividing that by u cubed du. And then you're going to simplify. Hopefully we're good enough at this now, especially with integer exponents, that we don't have to pull this out and do it separately. U squared divided by u cubed is 1 over u, which I'm going to leave like that because that's the special case where n equals -1. And then we'll have minus 2 times, and then you'll have u squared in the denominator. So I'm going to write that as u to the -2. And then when you take 1 and divide it by u cubed, you'll still have just u cubed in the denominator. So write that in the numerator as u to the -3rd. So we haven't actually integrated yet. We've just rewritten the expression so that we can use the power rule with u. Now we'll integrate. The integral of 1 over u is the natural log of the absolute value of u. For u to the -2nd, increase the power by 1 and divide by the new exponent. Same here, increase the power by 1, divide by the new exponent. Don't forget to add c. Now note that both of these signs are going to change because you're dividing by a negative. So you'll have plus 2 over u minus 1 over 2u plus c. And now you can back substitute for x. We know that u is x plus 1. You're going to take the natural log of the absolute value of x plus 1 plus 2 over x plus 1 minus 1 over twice, don't forget your parentheses, the quantity x plus 1. Oh, I just realized this. I forgot to square my u. It wouldn't make sense to have 2 linear factors in 2 different denominators. So this was u to the -2nd. So that should go to the denominator as u to the +2nd. I had it to the first. And then this quantity will be squared right here. Okay. There's something I like about this next example. I was just considering skipping it, but I just can't do it. I mean, I can't skip it. I can do the example. There's just something I like about it that I feel is instructive. It's just different. And then we'll do some trig ones after this. Good. This will kind of be our last one of this type before we do some trig problems. All right, let's do this one. All right, so this is the quantity x to the 5th plus 5x cubed times the square root of x squared plus 1 dx. I think sometimes it may be harder to tell which is the inside function because you have parentheses and you have a radical. And sometimes with integration, you just have to start trying stuff and kind of seeing where it gets you. I know that sounds terrible, but really that's the process for integration. And you're going to find that especially in Calc 2. You just got to try something and kind of see how it goes. But I mean, how else are you going to create the radical? You can create this piece, but you can't really create a radical out of thin air. So that should be leading you to letting u be the radicand, x squared plus 1. Okay, so this is good. If u is x squared plus 1, you might want to rewrite this and just sort of start building it. My suggestion to you would be to factor out this x cubed and look at this quantity without having to focus so much on these additional factors. So if you factor out the x cubed, that leaves you with x squared plus 5. And now we have u under the radical, but we haven't subbed out the dx yet. So we're going to have to do that. But this is what we've got so far, which is a mess. We can't have two different variables and the same integral in this case and evaluate it. Okay. But let's go ahead and find du because we want to sub out that dx. So du is 2x dx. 1/2 du is x dx. Okay. So we're just going to have to start building this thing piece by piece. If we know that u is x squared plus 1, well, look what you have here, x squared plus 5. We can also say something about x squared, by the way. Maybe we should do that also, because this kind of brings us back to what we did in the last couple of examples. We can say that x squared is u minus 1. So that's something we can do. Yeah, let's go with that for a minute. Okay, let's focus back on what we have and what we're trying to get to. Notice how 1/2 du gets us to x dx. Well, I don't actually have an x dx, but I can make one. I mean, I have it. It's just currently tied into this product. Let's take it out. Let's turn this x cubed into x squared. Now, I can't just get rid of it and forget about it, but what I can do is place it next to the dx to make it a little bit more obvious what's happening here. Because if I know that x dx is 1/2 du, then I can make that substitution. And if I know that x squared is u minus 1, I can make that substitution. So this started out looking a little bit wild, but by rewriting it and sort of just focusing on each individual piece, we were able to sort of transform this. Now, we still have to work on this piece. I don't have an x squared plus 5. I do have an x squared plus 1, however. And if I wanted to create a function u that would correspond to x squared plus 5, I could, and I want you to be careful with this. Notice that I'm not playing around with the du and the dx by adding things ever. We've only multiplied and divided. But when we're looking at the expressions themselves, not the du dx, but the u and the x, we can play around a little bit with these. For instance, if I wanted to create an x squared plus 5, I could take x squared plus 1 and then add 4 more to it. But it's an equation. What I do to one side, I have to do to the other side. So I added 4 on each side. I haven't changed anything. Now I can say that u plus 4 is x squared plus 5. So all kinds of crazy stuff is happening here. So I have u minus 1 times u plus 4 times the square root of u times 1/2 du. And now I've accounted for everything. I know it doesn't seem like it because it all happened so fast. Maybe it seemed fast to me. But I can write this now as u minus 1 times u plus 4 times, if you want to write this as u to the half, we can go ahead and do that. And then the 1/2 du, well, I'm just going to take that 1/2 and put it out front. And then I'll pop the du onto the end. And if you need to pause this and look at it more and process it, do that, because sometimes substitution can be tricky. It's true. All right, let's simplify as much as we can and then integrate, because this right now we can't work with. We don't have a product rule, and I can't just take the integral of each factor. It doesn't work that way. Okay, so I'm going to FOIL here. I'm just going to move this 1/2 out front because it'll just look better there for me. U squared plus 4 minus 1 is plus 3u minus 4 du. Now you can multiply the u to the 1/2 into your trinomial. 2 plus 1/2 is 5/2. 1 plus 1/2 is 3/2. And then for the last term, we'll have 4u to the 1/2. Now we're ready to integrate. Increase the exponent by 1, divide by the new exponent repeatedly. And if you feel like you're getting pretty comfortable just multiplying by the reciprocal of the new exponent, that's fine, do that. But I'm the teacher and I want everything to make sense. So I'm going through the additional steps to make sure it's really clear, especially since we're asynchronous and I can't take questions on it asynchronously. So I have 2/7 u to the 7/2 plus 2/5 u to the 5/2. When I take 4 and multiply it by 2/3, I'll get minus 8/3 u to the 3/2 plus c. And I'm going to simplify this further by multiplying the 1/2 into the parentheses. When I do that, I have to distribute it to each term, all 3 of them. In the first 2 cases, the 2's will cancel. So I'll be left with 1/7 u to the 7/2 plus 1/5 u to the 5/2 minus, now with these 2 terms, 8 has a common factor of 2, so I can go ahead and cancel out the 2's, and that leaves me with minus 4/3 u to the 3/2 plus c. Did I lose something? Yes. Sorry, I keep losing things. Sorry. This 3, I lost the 3. That's what happened. Sorry about that. So that means 2 times 3. And then that makes this a 3/5. Because the 2's canceled. Did I lose anything else? No. All right. Okay, so if you did not catch that, I had a 3 and then I got carried away and lost it. So I brought it back. And then the last thing you need to do is just back substitute for u. And that was a long time ago that we had u. So I'll remind you of what it is. It was x squared plus 1. So I'm going to sub that back in for u. See, now if you did something like that on a test where you forgot to jot down your 3, that's when you would say, oh, I made all these stupid mistakes. But you know what happens? Honestly, sometimes when I see stuff like that, I just circle it and put an arrow down. Like, it was there, clearly. You just lost it somewhere. Usually I don't get too worked up over stuff like that. Okay. Terrific. So that's that one. Let's do some trig ones. So that was about as hard as those are going to get for that particular type of problem with the double substitution. Okay. Example 8. This is the integral of the cosine of 7x plus 3 dx. Now, for a lot of these trig ones, the inside function is going to be easy to catch. For instance, you know, it's not just cosine x, it's the cosine of some function of x, 7x plus 3. So that's going to be your u. Some of these will be trickier than others, just depending on how the actual function's written. Du is 7dx. Well, we don't have 7dx, we just have dx. So we're going to have to divide that out. 1/7 du equals dx. But now I can rewrite the function in terms of u. When I rewrite this, I can write it as the cosine of u times 1/7 du. And again, this is not the way that I would leave it before I integrate it. I mostly just want to make sure that you understand where everything is coming from. So the dx is the 1/7 du. And then we already said that u was 7x plus 3. So that's where we got cosine u. All right, so I'm going to rewrite this one more time. I'm going to put the 1/7 in front, and then I'll have cosine u du. And now we can integrate this the way we normally would have in 4.8 or in 5.3 or wherever we last saw this. The integral of sine, positive sine, is positive. I'm sorry, the derivative of positive sine is positive cosine. So we can go ahead and write this as 1/7 times the sine of u plus c. And remember, you can always check this by just making sure that this function's your derivative, and here's the original. And then back substitute for u. I'm sorry, for x. So you'll have 1/7 sine 7x plus 3 plus c. Example 9 is the integral of x squared times the sine of x cubed dx. And again, these can be slightly trickier with finding the inside function, but in this case, you're not just taking sine x, You're taking sine of x cubed, which is a function of x. So u is going to be that inside function x cubed. And again, one thing that should tip you off to that also is the fact that the derivative of u would be 3x squared. And you do have an x squared sitting outside here. So that's usually an indication of kind of like, okay, they're setting me up to succeed here. The other piece is there, so it kind of guides you to what u should be. Well, we don't have 3x squared dx, we just have x squared dx. So remember, your x squared dx in this case gives you 1/3 du, and then you have the sine of u instead of the sine of x cubed. The 1/3 I'm going to put out front. Then I'm going to have sine u du. And remember, it's okay, you didn't lose anything. The x squared, I know it seems like something is missing. It's not. We accounted for it. X squared dx is 1/3 du. You don't need the x squared anymore. Don't freak out. I know it looks too simplified compared to your original, but everything's there. Okay, now sine needs to be the function that is your derivative. So sine is the derivative for negative cosine because the derivative of cosine is negative sine. So your original function was cosine u, but negative. And remember, you can go back and check it. So had you said it was just cosine u and you forgot the negative, well, you know that the derivative of cosine is negative sine. You don't have that. You have positive sine. So it must be the case that your original function was negative. And I did give you a list of those that you can always refer back to. In 4.8, I gave you a big list. I said something like table 6 on page 344, maybe something like that. Back substitute for x. All right, that was example 9. Example 10. Okay, so example 10 is a specific type of problem. And I want you to do it the way that I'm showing you. Technically, your book has a formula for this. I'm not going to be testing you in Calc 1 over your ability to use a formula to integrate a function. I don't know if the formula is in 5.5. It might be. I want you to do it the way that I'm showing you. Whoops. All right, so without further ado, example 10. This is the integral of the tangent of 3x plus 1 dx. You don't know of a function that is a derivative, that has a derivative of tangent. Now, what you might try to do automatically with something like this is you might look at this and say, okay, well, let's try u equals 3x plus 1. But when you do that, you end up saying, okay, no big deal. Du is 3dx, 1/3 du is dx. So 1/3 tangent u du, everything's accounted for. 1/3 tangent u, 1/3 du. Okay, it's dx. And this is a fine substitution. It is a fine substitution. However, now you're stuck because you can't think of a function that has a derivative of tangent u. And that's the problem with integration. You can't just force it. You're going to have to fit some sort of form. I know that tangent has a derivative of secant squared, but that doesn't help me here. I know that secant has a derivative that's secant tangent. Again, I can't just create a secant out of thin air. So what you're going to do is, if you want, you can keep this substitution. It's not a bad substitution. You can keep it if you want to. But you're going to have to rewrite the tangent of u as the sine of u over the cosine of u. And then you've got du here still. Okay, now if you're just like, wait, she just made this way more complicated. Actually, I did not. But you will have to do like a double substitution in this case. And I'm going to show you some more double substitutions. Are they coming up right after this? No, but soon. But this is the way that I want you to work on these tangent integrals. The next thing I want you to do is rewrite this as another substitution. You can switch your variables. And I hate to tell you that I always use w, because I've already used u. I can't use u again. It doesn't make any sense. We can say that w is your denominator cosine u. And if you're wondering why would she do that, well, the derivative of cosine u is negative sine u du. And hopefully we're starting to pick up on this now. I have a sine u du. But I can get rid of that negative by dividing it out on both sides. And now I can make a second substitution here. So for these tangent problems, turn it into sine over cosine and let your denominator be your other variable that you're subbing out. So now I can write 1/3 times the integral of sine u du is negative dw divided by the cosine u I said was w. The reason I said I hate to use w is because I don't like saying dw. For those of you who grew up watching Arthur, I don't know, there's something about dw that is just like, I don't want to talk about dw. Maybe I should start switching to v, and then I won't have to say dw. There's just something about dw that makes me want to laugh. I don't know. All right, negative 1/3 times the integral of 1 over w dw. It's just a standard variable that you would use anytime you're making a double substitution. So negative 1/3 times the natural log of the absolute value of w plus c. Now you're going to have to back substitute twice. W is the cosine of u, but u is 3x plus 1. So watch this. Negative 1/3 times the natural log of the absolute value of the cosine of u plus c equals negative 1/3 times the natural log of the absolute value of the cosine of 3x plus 1 plus c. Okay. So do not use a formula for tangent integrals. I'm even going to write this down because I've said it. I'll continue to say it, and I'll still have students say, like, well, it's telling us to use this formula. No, not in Calc 1. You're not using formulas. Do not use a formula for tangent integrals. So if the book gives you a formula, I'm not accepting it on your test. If I give you a tangent integral, this is what I expect to see you do. Okay. It's good for you. Okay. Example 11. If you're wondering how many more of these does she have, I believe I have 15 total, so we're getting there. Yeah, I have 15 total for today. So we're 2/3 done. Secant squared x times tangent to the 7th x dx. Okay. Now, this one's a little bit on the trickier side. And that's because secant and tangent, well, the derivative of tangent is secant squared. I just gave it away. The derivative of secant is secant tangent. So you see secants and tangents, and you're kind of like, well, which one do I want to be the inside function? And a lot of times, just like when you're using the chain rule when taking a derivative, it's helpful to write this so that you can see a quantity that's being taken to a power versus this standard like kind of shorthand notation. But I'm going to leave the secant squared by itself because I want to just show you what I want you to do, not like the way that this could look so confusing. Well, if you write it like this, you can see that your inside function could be tangent, and the derivative of tangent is secant squared. And then you would have u to the 7th du. So for problems like this, you might want to just sort of be like mentally formulating a plan before you actually start writing down u's. Otherwise, some of you might just start writing down u equals and then du equals, and then maybe finding out that it works, maybe finding out that it doesn't work. So, and that's fine. I honestly was one of the students who was just like, let's try this, let's try that, let's try that. So if you are one of those students, I'm certainly not trying to say that that's a bad thing. Okay. So we'll let u be the tangent of x. Du is the secant squared of x dx. Now we're going to take something that looks a little more complicated and really simplify it down. Secant squared x dx is du. Tangent x to the 7th will become u to the 7th. So when we rewrite this in terms of u, it just looks like u to the 7th du. That's it. And again, don't get bogged down in like, oh my gosh, this looks way different. All you have to do is just make sure everything's accounted for. If it is, then you're good to go, and you can integrate and back substitute. 1/8 u to the 8th plus c is 1/8 tangent to the 8th of x plus c. Oh, example 12 is another one I'm debating, but I feel like there might be one on the homework that's kind of similar to this. That's good for you, so maybe we'll do it. Definitely a little bit on the trickier side. Trying to see what was like the most tricky thing. Oh, yes. Yeah, so I have this, and then I have an exponential, and then I have some inverse trig. So this is another double substitution, and anytime you're dealing with a double substitution, those are going to be trickier. So this is example 12. So this is the integral of tangent x times the natural log of the cosine x dx. And this is definitely one that you're going to want to play around with a little bit. For instance, I think we would pick out the inside function cosine x. I mean, what else could it be in this case? So let's let u be the cosine x. And then du is negative sine x dx. Well, then you're looking at this and you're like, okay, I don't see negative sine x dx, so how's this helping? Well, you're going to create it because you have a tangent here and you don't know what else to do. Now, let's swap out this negative just because it's bothering me. So the tangent of x becomes the sine of x over the cosine of x. And then I have the natural log. We'll just write it all in terms of x for a second, and then we'll start to sub in a minute. Okay. All right, so I'm going to have the natural log of u, and then the du is going to become, or I'm sorry, negative du is going to become sine x dx. So we can start to replace things as we see them. Let's see. The sine x and the dx together will become negative du, and then this guy will become the natural log of u. Now, I'm going to leave the negative in front. I'm going to leave 1 over cosine x because there's nothing I can do with this cosine x right now. And then I'm going to have times the natural log of u, and then du. Okay, so it's not great, but it's okay. However, notice that even though you still have this cosine sitting here in the denominator, yoink, cosine x is u. So you actually can rewrite this whole thing in terms of u right now. So just swapping out cosine of x with u. And a lot of times it just helps to do this in chunks, because if you try to do it all at once, stuff's going to get lost. But you might want to double check, make sure everything's accounted for. I'm telling you that it is. Use your best judgment. Now, this is an exercise that you could have seen on its own. You might see on its own somewhere else in 5.5. It would have been just displayed to you like this, probably using x's instead of u's. But this is actually a pretty standard u substitution problem. However, since we obtained it by doing a u substitution, we can't keep using u. We're going to have to use w. And if you're kind of thinking in advance of what's going to happen here, well, this one is not a situation where you're going to be using an inside function per se. You're trying to match up some sort of function and its derivative. Well, I know that the derivative of the natural log of u is 1 over u du. So this is not going to be one of those cases where you have this very clear-cut inside function that you're going to let be that substituted variable. In a case like this, we're going to let w equal the natural log of u, and then dw is 1 over u du. So this is just an example of one of those substitution problems that isn't quite as cut and dry. But the more you see, the more you're going to know, the more you're going to become familiar with. Honestly, with integration, it's just about seeing more examples, seeing more techniques, and then every time you see something new, it kind of, you file it away, and eventually you'll come to a time when you are like, wow, there was this thing and it seems familiar, and I think I did this. You're going to go back through your notes, you're going to leaf through, and you're going to find it, and you're going to try it, whatever it was. And maybe it'll get you on the right path, and maybe it won't. Integration is a process. So let's do a substitution here. So the natural log of u is w, and 1 over u du is dw. So you have the negative integral of w dw. And that's going to be easy for us to integrate. So this will be negative 1/2 w squared plus c. Back substitute for u, negative 1/2 ln u squared plus c. And then back substitute for x. Negative 1/2 ln cosine x, quantity squared. Make sure you're careful with your grouping symbols, plus c. I'm trying to get it all in there. So that was definitely a little bit of a trickier one. But now that you've seen it, hopefully part of that will stick with you. The next one I'm going to show you, again, is also kind of tricky, and it's one that you probably wouldn't have caught right away. Maybe some of you would have, but it's one that, oddly enough, like it shows up more often than you would think. I'm going to write it down. I'm going to grab a jacket because I'm, for some reason, like freezing over here. But you write this down, and I'll be right back. E to the t times e to the 2t plus 2 e to the t plus 1 dt. Be right back. Oh, it'd be helpful if you could see it, right? Be right back. Okay. E to the t times e to the 2t plus 2 e to the t plus 1. Okay. Again, this is one that's not very obvious. I'm going to show it to you, though, because this quantity seems to just show up a lot in calculus, and I want you to recognize it the next time you see it. It's this one right here. This is actually something that you need to factor, but it's not that obvious. So I'm going to make a parallel between this and a polynomial that maybe you would have recognized. So let's say, recall x squared plus 2x plus 1 equals x plus 1 quantity squared. So this is a perfect square trinomial. And you can factor that by saying it's x plus 1 quantity squared. And if you don't remember the formula for a perfect square trinomial, that's fine. You just are looking for the two numbers that multiply to give you 1 and add to give you 2. And those numbers are 1 and 1. So you'd have x plus 1 times x plus 1. That same idea will apply to this expression, except you're just letting x be e to the t. Now, if you let x be e to the t, then you have e to the t squared plus 2 e to the t plus 1. And this ends up being, by the way, e to the 2t plus 2 e to the t plus 1. Take a power to a power, you multiply the powers. But if we let that be true, that x equals e to the t, well, then we could say that we could factor it the same way as e to the t plus 1 quantity squared. Same idea. And if these two are the same, then I can say that we have this same expression again. So this is actually just in the form of a perfect square trinomial. It's just hidden. So whenever you see e to the 2t, you should be thinking about that as being e to the t squared. It's just that you take a power to a power, you multiply the powers. It's usually written as e to the 2t. But we're going to go ahead and factor this because we know we can now. I showed you how this works with the polynomial. And it'll work the same way with the exponential. So you have e to the t times e to the t plus 1 quantity squared dt. Okay, so the whole point was that they were trying to hide this, the fact that this is just a a quantity squared. But now you can clearly see an inside function, which is e to the t plus 1. And then du is e to the t dt, which you have. So e to the t dt is du. And then you have u squared for the other piece of this. So you actually have u squared du. And then you'll integrate that as 1/3 u cubed plus c. And then you'll have 1/3 times, sub that back in, e to the t plus 1 cubed plus c. Done. And I have 2 examples left. Sorry, I don't want my done to seem like it indicates that we're completely done because we have 2 examples left. Trying to figure out now, because I was going to draw a parallel between this and that example, that table I gave you, but unfortunately I didn't bring all of my chapter 5 notes down. I have it over here. You know what? I'm just going to rewrite it for you. So I reminded you the other day, and I'm going to give these to you again, the inverse trig formulas. So we had this one, and then we had the inverse tangent form, and then there was one for the inverse secant. It was x squared minus 1, sorry. Okay. It's important that we recognize when we're close to one of these forms. You'd be surprised how often these show up in Calc 1 and Calc 2. You'll have an integral that's very similar to this type. However, it's extremely important that we note the difference between this and a situation where we have x dx. Because if there's a variable in the numerator, this becomes a standard u substitution, where I have du over the square root of 1 minus, or the square root of u, I should say, in that case. And I want to talk a little bit more about just recognizing the difference between the two on Monday, because I'm going to give you an example where we'll have 2 terms, and one will be an inverse trig function and the other will be a standard u substitution. But we are going to work on 2 examples with these inverse trig functions. So you'll know it's the form of an inverse trig function if you see the denominator appear the way it does in any of these examples, and you just have a constant in the numerator. Now, of course, that would change if your variable expression changed, but as long as your denominator had some form of x squared in it, then you'd be looking for your derivative to be some constant dx, not a variable dx. And I'll see if I can come up with an example. You might see one on your homework, very possibly, that would be similar to this, form. Might not be. I have to think about that, if it pops up here or not. Definitely Calc 2. All right, example 14. This is the integral of 3 divided by the square root of 25 minus x squared dx. And I do have a note here to kind of go along with what I was just saying. So this is not the same as taking the integral of 3x divided by the square root of 25 minus x squared dx. Note the difference. They look extremely similar, and you might look at the denominator and say, oh yeah, it's some number squared minus x squared under the radical, totally inverse trig function, but it's not. So this function, if you were working on this integral, you would let u be 25 minus x squared, du is negative 2x dx, and then negative 1/2 du is x dx. And you would do a u substitution that way. So you would say negative 3/2 times the integral of du divided by the square root of u. Not the same thing as what you have here. Notice that this u substitution doesn't work here because if you take du, you get negative 2x dx. Well, you don't have an x dx. And you can't just divide it out. That doesn't work. You can only multiply and divide here by constants, just to kind of play around with that not arbitrary constant, but the constant multiple. This works because you have 1 degree less in your derivative. This is 2 degrees less. This is x to the 0 power. Not the same. Make sure that you understand the difference. This is a u substitution. This is in the form of an inverse sign. You're just going to have to do a little bit of work on it to make it look like that. Now, when I say you're going to have to do a little bit of work, that means that you need to fit it into this form. The first thing you need to do to fit it into this form is to make this 25 a 1. We have to have it be a 1. Otherwise, we're not going to be able to match this formula. Okay, now we can do that. I'm going to move the 3 outside because it's going to distract me. And I'm going to move the dx into the numerator. Now, if I'm going to make the 25 into a 1, I'm just going to divide it by 25. Seems simple enough, right? However, if I divide this term by 25, I have to divide that term by 25. Now, what I've really done is I've divided by the square root of 25 in the denominator. What I do in the denominator, I must also do in the numerator. You know what? I did it this way because it seemed most intuitive to me. But now I feel like it's less intuitive for what you're doing in the numerator. That's fine. We'll just do it anyway. If we divided by the square root of 25 in the denominator, we'll do the same in the numerator. No big deal. Just make sure you include the radical and make sure it's in the denominator. What you do in the denominator, you must also do in the numerator. And then you haven't actually changed the expression. Now, the nice thing is if you'll get lucky enough to see this, you'll have a perfect square, and you can evaluate that as 5. And then that moves into the denominator as 3/5. Now, be careful what you do with this radicand. 25 over 25 is 1. That was the whole point of dividing by 25, is that I just wanted to get that to be a 1. What you want here is you want this to be a quantity squared. Right now it's x squared over 25. However, we can turn this into a fraction that's being squared. And the way that I would do that is I would square the x, and I would think about what quantity I would need to square to get 25, and that would be 5. So if I take x over 5 and square it, well, I'll get x times x, which is x squared in the numerator, and 5 times 5, which is 25 in the denominator. And if you're wondering, like, why did she do that? That doesn't really make any sense. What I want is for this to be a 1. This is just a function of x. Now it's a u substitution because I don't just have x, I have x over 5, also known as 1/5 x. So I'm trying to match this form. I'm close, but I don't just have x squared, I have 1/5 x squared. So now we can do a u substitution, and we'll say we're going to let u equal not just x, but 1/5 x. And that's how we will get away with that. And then du is going to be 1/5 dx. That means that 5 du is dx. So let's sub it out. There's my 3/5. Then I have the integral of, well, dx we already said was 5 du divided by the square root of 1 minus u squared. The 5's will cancel, and you have 3 times the integral of du divided by the square root of 1 minus u squared. Now you have exactly what you need for the inverse sine form. It's just that instead of x's, you have u's. So we'll say that we have 3 times the inverse sine of u plus c. And then sub out your u for x. And we had, where is it? Oh yeah, u equals 1/5 x. I'm staring right at it. Or x over 5, whatever you decide. All right, just have one more example, one more inverse trig function. Just trying to figure out how I'm going to go about this because I did this one in the way that I normally wouldn't do it. So now I have to do that all the time now to remember that. All right, last one for today. Example 15. This is the integral of dx divided by 5 plus 25x squared. Now, again, I'm emphasizing this because it's such a big deal. This is not the integral of x dx divided by 5 plus 25x squared. If I had this, I would say u is the denominator, du is 50x dx, and 1/50th du is x dx. And then I would make a u substitution, and I would say, okay, I have 1/50th times the integral of 1 over u du. And that would be very straightforward. I would have 1/50th times the natural log of 5 plus 25x squared plus c. But I don't have that. So I don't have this. This is a whole separate problem. I do this just so that I can make sure that you understand the difference between this and this. If I let u be the denominator in this case, I end up with an x dx. And the expression that I gave you, for example, 15, you don't have an x dx. You just have dx. And you can't get rid of the x. You can't divide it out. I mean, what would you do? Divide it out. Then you'd have 1 over x du. Then you'd have 1 over, and then you have to solve for x. It would be a giant mess. And I don't even know if in the end you would actually get anywhere good. I don't know. All right, so we're going to do this in a similar way that we did the last example. This is in the form of an inverse tangent. it's got a constant in the numerator divided by a constant plus some quantity that's being squared. Yes. If I were you, not, but you might want to rewrite this so that you can actually show that there's a quantity being squared. We can rewrite 25x squared as the quantity 5x being squared. And that's going to help us to get where we need to go. But first, we need to make this a 1. So the form I'm trying to match is this one. I just want to be able to sub out the x for u. If I'm trying to make this a 1, I can just divide it by 5. But what I do to one term, I have to do to all the terms. So I can take 5 and divide it by 5. And then I can take 5x, the quantity, and divide it by 5. And then in the numerator, I can also divide by 5. And then we'll kind of simplify our way down here. So now every term is being divided by 5, kind of the way that we would work on a complex fraction. I'm going to take this 1/5 and move it in front. That leaves me with just dx in the numerator and then 1 plus. Now we're going to have to work on this because I need it to be an entire quantity squared. We've done a lot though, so for now I want to just leave it there. If I want to make this quantity squared, then I need to write 5 as the square root of 5, because the square root of 5 squared is 5. And I don't want to change the actual meaning of the expression. 1 plus, all right, here we go. So the 5x is being squared, and I'm dividing it by the square root of 5. So nothing has changed. I still have a 5x being squared, but now I also have the square root of 5 being squared. The purpose of this is I just need to have this entire quantity being squared so that I can write my u substitution. Now, if this radical in the denominator is bothering you, you can always get rid of it. I mean, it's kind of up to you. 5 over the square root of 5, when you rationalize it, is 5 root 5 over 5. The 5's cancel, and you just get, whoops, the square root of 5. So you technically can do that, rationalize, and cancel. So if you prefer to do that, go ahead and swap it out. So this will be the square root of 5x squared. If you did not rationalize, that's fine. I just happened to recognize this as something that was going to look better if I rationalized it. That's not always the case. Sometimes expressions look more complicated when you rationalize them. But this one did not. But now you can see that we have this inverse trig, inverse tangent form that we're looking for. Dx over 1 plus x squared. We're looking for du over 1 plus u squared. Now we don't quite have it yet, but we're easily going to get it by letting u equal the square root of 5x. So whatever that expression in x is that's being squared, that's what we're going to let u be equal to. And then du equals the square root of 5 dx. That means 1 over the square root of 5 du is dx. Okay, and we're ready to sub it out. So this is 1/5 times the integral of 1 over the square root of 5 du divided by 1 plus u squared. Sorry, I keep doing that. And then, if you want, you can pull that root 5 out. You don't have to. Sometimes it distracts me, so I just want to get rid of anything that's not my exact inverse tangent form, which is now what I have. So I have 1 over 5 square root 5 inverse tangent u plus c. And it's 1 over 5 root 5 inverse tangent. Where was u again? Oh, there it is, the square root of 5x. Remember, it's the square root of 5 times x. It's not the square root of 5x quantity. The square root of 5 times x plus c. All right. So that was what I had to say for the substitution method using indefinite integrals. You're going to find that I'm going to post some homework. Some of it's going to be almost easy, where you're just going to be like, okay, yeah, obviously u is this, du, blah, blah, blah. And it's just going to seem kind of boring. And then there are going to be other ones where you're going to have to think a little bit more. I'm definitely going to put on at least 2 inverse trig functions for indefinite integrals if they have them. I'll have to check real quick. But you've pretty much seen what you're going to see. So refer back to your notes. They should be invaluable as you work through your homework. We're going to work on definite integrals on Monday, and we're going to use a change of variables formula for definite integrals to switch our upper and lower limits of integration to match u. So normally our limits have to do with x going from a to b, but if we switch our integral over to u, we're going to need to worry about where u is going. So we're going to do that Monday, and then we'll just, obviously, as we work through definite integrals, we'll just get a little bit more practice with the process of substitution for integration. So we'll do that Monday. And so Monday I'll have, like, I don't know, maybe 11 more examples for you. It's going to be great. Okay, I'm not going to waste any more of your time. I'm going to post some homework. Hopefully you are doing this before Monday. If you're not here before Monday, there's nothing I can do about it now. It's too late. But yes, work hard on this and let me know if you have any questions. I'm expecting a lot of questions on this. So make sure you're asking questions when you have them. That is all. I will see you on Monday. You guys have a great weekend, okay? We have 1 week to go. We're almost done. Hang in there.